So right in your 7th standard and 8th standard, what did you learn? They told us that light is a ray. And they told us something, rectilinear propagation of light. And what is that? Light will always travel in a straight line. Why? I always had this question. I was sitting in class and I said, why? Why doesn't it go somewhere else? Then they told me one more thing. The angle of incidence is going to be equal to the angle of reflection. And all three lie in the same plane. This was called the law of reflection. Okay, it's a law. You can't really question it, they said. But my question was, why is the angle of incidence always equal to the angle of reflection? Hey, that and all you're not supposed to ask. Right, because you're supposed to remember that, not ask that. They'll ask you, state the law of reflection, you'll state it beautifully. Angle of incidence equals angle of reflection. The angle of incidence is the angle made by the incident ray with the normal, and the angle of reflection is the angle made by the reflected ray with the normal. They all lie in the same plane. They'll give you 2 marks. You'll feel very good. But what happens if you ask the question, why? Okay, can you even answer that? Is there a hope to answer that question? But maybe there is. We can maybe go one level deeper and maybe answer why these two have to be true. Because if you really go into it, it all stems out of one particular understanding about light. Now, why light does that, we don't know. And that is this. Light is in a hurry. What do I mean by that? Given 2 points, light somehow chooses to take the quickest path between them. And make it very clear, I'm not saying shortest path. I'm saying quickest path. And we all know sometimes the shortest path is not the quickest path. Anybody who lives in a city knows this, right? The shortest path between 2 points is a road, which takes you very cleanly towards it. But if there's too much traffic on it, you might take a much longer path but reach a lot quicker. So it's not really true that, shortest path is quickest path. So light always takes the quickest path between 2 points. Now you might ask, why is that true? Then I'll say, I don't know. Nobody knows. Yeah? We can answer that question in a little more deep manner if you go and treat light as a wave, but we won't do that right now. Right? So we will say that light will take the quickest path. And if you remember this alone, or if you accept this alone, we'll be able to explain everything else in this chapter using this one idea alone. And what is that? Given any 2 points, light will take the quickest path between the two of them. And if you accept this, trust me, there is not a single thing else that you can't infer from this particular thing alone. And we'll show you how. Let us take 2 points within the same medium. Right? And we all know that light travels in the same speed in a particular medium. Right? Only when it goes from one medium to another, its speed might change. Now, why that happens, we'll go into it. So given 2 points within the same medium, what is the quickest path between them? It's also the shortest path, the straight line between them. So no wonder between one point and another point, light takes a straight line, because that's the quickest path. Does light want to take a straight line? Not really. Light just wants to take the quickest path. It happens to be a straight line. So what have we just proved? Rectilinear propagation of light comes out of what? Light's in a hurry. Light wants to take the quickest path. Okay, we've done the first part of it. What's the second part? Can we actually prove this? The angle of incidence is equal to the angle of reflection. Why? Why not something else? So if you were to be curious enough to ask that question, then let's see what we can do. It's a very beautiful thing. Let's start with a story. Let's say there's a pole here, and there's another pole here, a taller one. And let's say there's a crow sitting on this one. And there's a mouse running between these 2 poles continuously. Right? And the crow's nest is on the other pole. Now what does the crow want to do? It wants to take this mouse and carry it to its nest. And the crow flies in straight lines. So you might be beginning to guess what we're getting to with this. And the crow wants to do it as quickly as possible. Let us say. So we have a very simple situation here. So then the question is, where must the crow catch the mouse? Should it catch it when it's right close to that pole, very close to this pole, when it's right in the middle? Where exactly? How do we answer such a question? Think about it. Now, if you were to imagine the second pole and reflect that second pole on that road such that it comes down, you might be wondering why we're doing this, but you'll watch it in a couple of seconds, then look at what happens. What is the shortest part between that pole and this end of the pole now? It's a straight line that connects them. That's very clear, because between any 2 points, the shortest distance is a straight line. Now, why did we do this? Because these 2 triangles now are similar, which means that if that is the shortest path between these 2 points, then the exact reflection back must be the shortest path between these 2 poles, which is what we're trying to find. Because in this case, the shortest path is the quickest path as well. So where will it intersect? Where will the crow catch the mouse? The part where that line intersects the road, like you can see. Now, what if these 2 poles are of equal height? What happens? Watch what happens if these 2 poles are of equal height. You reflect it and draw a line. Where does it pass? Right through the center of that road. You reflect it back. Now what do you see? These 2 triangles are congruent. You already know what congruent triangles are, which means that these 2 angles are going to be equal, and those 2 angles are also going to be equal. And what have we just proved? That the shortest path between this point and that point touching the mirror is going to be the point such that it hits the center of that mirror. Right? Why am I talking about mirror all of a sudden? Because right now our story was a crow taking a mouse and carrying it to the other pole. Right? Now when we do that, we've realized that if the crow was light, then what does this become? Light also wants to take the quickest path. So light will go through the center and reach the other side if this was a mirror. Of course, the shortest path to take in general would be the straight line connecting them, but we're talking about the ray of light that gets reflected. So the question is, the ray that has to touch the mirror and still go there, and then which will be the quickest path. And what is it? We just proved it's the center point. And by proving that, what have we proved? The angle of incidence equals the angle of reflection. And we have not told it as a law, but we have told that, does light want the angle of incidence to be equal to the angle of reflection? Not really. All that light is trying to do is to make it so that it takes the quickest path. And it so happens that that quickest path is such that the angle of incidence is equal to the angle of reflection. So if you notice something, till now, we've proved already that rectilinear propagation of light, or that light travels in straight lines, can be proved using just one assumption: light's in a hurry. And angle of incidence equals angle of reflection can also be proved using the same thing: light's in a hurry. Light wants to take the quickest path between any 2 points. Now, we have told it in a very general manner, or a very funny manner, as light's in a hurry. There's a name for this. It's called Fermat's principle of least time. In other words, Fermat stated that between 2 points, light will always take the quickest path. And that's called Fermat's principle of least time. And that is going to be our focus, because with that one statement, we're going to prove everything that we can do in this entire chapter called ray optics.